Dear Bob, it is a great pleasure to be here at this important event. 80 years is 4 times the age of Hippo. Happy birthday and many more happy years to come. I want to talk today about neutrons and texture, which is a topic which has kept us together for many years. It didn't actually start with us. It started with Brockhaus already in 1953, the first one to use neutron diffraction to get texture information. Now, why would we want neutron texture measurements compared with other methods such as X-rays and electrons? And the main advantage is that neutrons penetrate material, most elements very easily, and therefore you can use large samples, and in polycrystalline materials get good averaging over large volumes. For me, it started in 1985 at ILL in Grenoble, where they had this interesting detector which had a continuous 1D spectrum. So you could measure a spectrum at once, and then you could rotate your sample and you get different intensities indicating that in different directions of a sample you had differently oriented crystals. And this then became a foundation of a project to use a sample here of experimentally deformed limestone, about a cubic centimeter in size, and measure that at different facilities, such as at ILL, at ULEC with a single crystal diffractometer, at IPNS and at LANL. And what was amazing for me is that the results were for all very similar, which is different for, like, for example, a pole figure goniometer with X-rays, where you have a lot of problems with absorption and also with corrections for tilt, which have to be taken into account. Well, this is what about the time, 1984, where I came for the first time to Los Alamos to a meeting, and I was asking if I had similar facilities here, and Phil Vergamini took me down to the Los Alamos Canyon with his old neutron radiation facility. But about the same time, also the Lujan Center in at LANL got finished in 1985, and that's where we started experiments on the single crystal diffractometer at LANS, where you have a 2D intensity collection of and at the same time you use time of flight neutrons. So at each point you don't just measure a point intensity, but you measure a whole spectrum from which you can derive the orientation of the crystals. We measure this both at LANL and at Argonne with Art Schultz, here with Al Larsen, and the results were very convincing. In fact, 1986, this was an important time for Bob and Al, where they came out with the first version of GSAS, which has since been used by thousands of use of neutron diffraction experimentalists to process data. And then about 10 years later, Bob incorporated texture analysis by Rietveld refinement in GSAS, which also has been very widely used. It was around this time, 1987, that there was a call for new proposals for beamlines at LANS, and I got together with colleagues and from different places, different universities at UC, and we put something together, a proposal for a research, University of California Materials Research diffractometer, together with Kristin Bennett, who was then a postdoc at Lujan, and Bob van Dreele, who was the technical director and really designed most of the instrument. This was quite a fantastic instrument because it combined now many detectors distributed over many places on this instrument, very large instrument. So each detector records a spectrum, and the position of these detectors records the diffraction relative to the sample position. So it is ideal to measure preferred orientation of crystals in polycrystalline materials. It was actually Kristin Bennett was responsible for that, to call this HIPPO and not UCMRD, which nobody knows what it would be about. And it stands for high pressure preferred orientation. Well, this was a long time with meetings and writing proposals, lots of paperwork, budgets, timelines. But in the end, we did convince the committee and it was approved. And we went ahead and started building it in 1998. Here is Bob, together with Kristin, in Oakland at the factory where we built the sample chamber, and the panels were built at in workshops at UC Berkeley. Just to mention, Kristin Bennett has also quite a remarkable career, not just at Los Alamos, but the latest one is to climb mountains in the Himalaya. And 2 years ago, she climbed Mount Everest and still goes every year and climbs another high peak there. So HIPPO is born, and just a picture to show you the sample chamber. I could almost climb into it. So you can have equipment which heats the sample or has different atmospheres or different cooling in the sample, and a sample changer where you can put many samples in, and it automatically measures and changes them. So we have many spectra, like about 400 spectra, 48 detectors, and then we rotate the sample around one axis. And from that, with a Rietveld refinement, we can extract not just texture, but what the material is like, what phases there are. And this can be done with GSAS, like we have the 1997 paper, and the same year there was a paper for another software called MAUD, which can be applied to this. Our first paper with HIPPO data came out in 2003. I should just mention this is not the only diffractometer which is largely developed, dedicated to texture analysis, and another one is Scott at GINR in Dubna, which Ole Meyer was responsible for, that actually became finished quite a bit before Hippo. And you see this huge ring with detectors that can actually handle samples which are up to about 5 centimeters in diameter. So it is there along the Volga and just behind the statue of Lenin. Here is an example of Hippo data collected and compared with data for, this is again this round robin limestone, with data for ILL, now the D20, a more recent diffractometer, and you see again a very similar pattern. Very similar pattern, except that if you look at the Hippo measured this one on top in 20 minutes, while in ILL it took about 4 hours. So texture analysis, now what is remarkable in Hippo, that we can heat samples in situ and look at the texture changes. And we applied this to iron, which is BCC at low temperature, and heated it to 800 to about 1,000 degrees, and then it became FCC and cooled it again. So you see how the spectrum changes, and then how the texture changes. So first at low temperature in PCC, we have a maximum at 111. And then it switches at 950 degrees in FCC to a maximum at 110. And remarkably, as you cool it again, it goes back more or less to the same texture as it was before. So there is a memory effect. And on this slide, I show you this. We can not only apply to metals, but also to rocks. Now, quartz goes through a phase transformation from low quartz, which is trigonal, to high quartz, which is hexagonal at about 570 degrees. So first you have this is now a quartzite, polycrystallic quartzite rock, which is strongly textured. C-axes are here, and then these rhombs indicate the trigonal symmetry. As you go to 620, it switches, it becomes hexagonal, and so there is no longer this trigonal symmetry. And remarkably, as you go back to cool it again, then you see it becomes trigonal again. And it keeps a memory, it goes back almost to exactly the same position. And the reason for this memory, this orientation memory, is probably the shape, so that grain boundaries, if you change it after its grain boundaries, the old grain boundaries impose stresses, so that it goes back to the same orientation as you had before. Well, these are just a few examples. Thank you, Bob. Without this, would have never been possible. And all the best in the future.